Okay, I am back after like a couple, like 2 minutes, because I realized what's happening here. So what we need to prove here is that we need to prove that sk is equal to sk plus I mod n. And that's all we need to prove, because if we prove this, then that proves this statement up here, the larger statement. Because if we know that s equal, I guess it doesn't, because it doesn't, no, yes it does. So if sk is equal to s plus k, if s is equal to s plus s of k plus I mod n, then basically you can just keep adding I as many times as you want. Basically, that's the punchline here, is that this statement, which implies sk equals sk plus mi mod n for all m and z, for all integers m. Okay. And I guess, so now thinking through this, it certainly implies like when m is a positive integer, like okay, when it's 0, it's obviously true, because that's just sk equals sk. But if you this fact will hold true for any integer k between any possible index k of s. And so if this holds for s of k, meaning that s of k equals s of k plus I mod n, then it also holds of, you could just take that resulting number and add another I mod n, and then add another I mod n, and then add another I mod n, and all of these will give you like the same value. And so this is going to be, and so it's certainly going to work for all positive values. And okay, this is going to be very hand wavy, but the reason that it also applies for negative integers is that this is really a group theory proof. And we're working in the integers mod n. And so what happens is like mod n, any multiple, any positive multiple, like any negative integer multiple of a number is also a positive integer multiple of a number. Sorry. Let me write this out explicitly, just as an aside. So let's put it here so that it's to the side. Okay, so mod n, or let's use the group theory notation. In z mod n z, for all m, if m is an integer greater than 0, no, actually, let's write it this. If m is an integer less than 0, then there exists an integer lmn p greater than 0. Greater than 0, such that mi is equal to pi. So basically, basically the thing is, when we're working in modular when we work in modular arithmetic, negatives don't really matter because you just wrap around and start at the beginning, so you're positive. So if you take like some negative, and I should say congruent here, because it's congruent mod n, because this is all taking place in z mod nz. The integer mi will certainly be different from the integer pi because m is negative and p is positive, and so unless I is 0, these are going to be different. But they're going to be equivalent mod n. And this is just because yeah, a negative, multiplying by a negative is the same as like applying by, you're just sort of like taking the inverse a number of times. And like the inverse is actually like a positive number. Yeah, I'm being very hand-wavy here. I didn't write this out, so I'm not going to go into this further. But basically, because of the way that modular arithmetic works, if sk equals sk plus I mod n, then this sort of generates this, because starting from k, you get all, and we'll actually talk about this later on in the proof, but it's we're talking about the subgroup generated. This is sort of like an affine subgroup of generated by I offset by k. But we'll get to that later. But the point is, this proves this. So all we need to prove is this. And this statement follows from 1 and 2. And it's just the two cases here. So here, sk equals sk plus I, which is equal to s of, so this is going to be equal to s of k plus I mod n, because k plus I here is, well, we know that k is strictly less than n minus I. So this is going to be strictly less than n minus I plus I, which equals n. So this means that k plus I is an integer within the, k plus I is an integer less than n. So it is a valid index of s. And so because it's a valid index of s, taking mod n doesn't actually change anything. It's just literally like you don't, since k plus I is already an integer which is between 0 and n minus 1, taking mod n doesn't remove, it doesn't change the value at all. So k plus I is equal to k plus I mod n here. Okay. Let's do the other case where k is greater than or equal to n minus I. This follows a little bit indirectly from fact 2. We need to do another step here. So if k is greater than or equal to n minus I, we're going to write k is equal to n minus I plus some integer q, where what are the possible values of q? It has to be it has to be at least 0, because the case of 0 is just k equals n minus I, which is the minimum value of k. How high can it go though? So k is any valid integer, any valid index of s which is greater than n minus I. So it can only go up to n minus 1, right? Oh, wait a minute. Yeah, k can only go up to n minus 1. So that means that q would go up to I minus 1. Because when q equals I minus 1, we have k equals n minus I plus I minus 1. And so the i's cancel, and you just end up with n minus 1. Okay, good. So write this. So now we have sk is equal to by definition, n minus I plus q. Q is defined this way. And then by fact 2, we can, so now we can apply fact 2. But see, we have this L here. I probably should have just used L. You can see L satisfies the exact same thing. And so we can apply this, and so we get S of Q. There we go. That's just by applying fact 2. Okay. All right, so now I need to go back to my original notes for the original proof of this. Okay, so now we can continue from here. Note that k, let's see here, k plus I, is that what we're looking at? So we have k is a value from n, it's somewhere between n minus I and n minus 1. So if we add, I to it, k plus I could be as small as n and all the way up to n plus I minus 1. And this is certainly going to be a subset of the indices from n up to 2n minus 1, because I is going to be strictly less than n. Okay? So what this means is that k plus I, basically what this is saying is that k plus I is going to be some number which is at least n, but not more, but at least n, but less than twice n. Which means that if we want to apply modular arithmetic, mod n, we only need to subtract one copy of n in order to get k plus I into the range of integers from 0 to n minus 1. So what this means is that k plus I mod n is going to be equal to k plus I mod, I'm going to write it this way. K plus I is equal, k plus I minus n is in let's write this. K plus I is equivalent to k plus I minus n mod n. And we also have k plus I minus n is an integer between 0 and n minus 1. Okay. Thus, what we have is sk equals sk minus n plus I. Is that what we wrote? K minus n plus I. Ooh, where did this come from? Hold on, give me a second. Just 1 second. Oh, right. Sk is equal to Sq and Q, since K equals n minus I plus Q, Q is equal to K minus n plus I. Or let's write it as K plus I and minus n. All right. So now this is sk plus I mod n, because that's what we, because k plus I mod n we just showed is equal to this, okay, because of the fact that k plus I bleeds over into here. And this is basically like, if you think about k greater than n minus I, we're considering the indices c, d, e, and f. So these are the, so here k is the indices representing c through f of this example. And basically what all this is saying is, because this second half of the string s is in the second copy of s in the larger string, you can use that to your advantage to get this identity. Okay, so in both cases we have sk equals sk plus I mod n. And then by this argument which I outlined, this gives you that sk is going to be sk plus mi mod n. And so basically what that means is, if you take a, so what is this really saying? So this is pretty significant. So what is this telling us? What this is telling us is that if you start at an index in the string s and you take the offset, then taking that offset mod the length of the string s is going to give you all characters which are equal to each other. So let's say, for example, here we have this example of I equals 4. So here we can start at index A, and then we can increment 4, 1, 2, 3, 4 to E. And then this is telling us that the character E is equal to the character A. And now we can increment by 4 again, 1, 2, 3, 4, because we wrapped around because of modular arithmetic. And then, so this tells us that E equals C. And then we can increment by 4 again, 1, 2, 3, 4, we wrap around by modular arithmetic, and we're back at A. So we get this cycle where we go from A to E to C to A to E to C. And so we get this A, C, and E are all equal characters in the string. And basically what you can do is you can go from there, and you can kind of see where this is going, because if A equals C equals E, then you can like take that pattern and shift the whole pattern over by 1, and you'll have B equals D equals F. And that's true from this again. You can start, instead of, so saying A equals E equals C, that process we did was starting with K equals 1, or K equals 0. If you do K equals 1, you're starting at B. You get B, 1, 2, 3, 4, F, 1, 2, 3, 4, D, 1, 2, 3, 4, B. Okay. So we have A equals C equals E, and B equals D equals F. Okay. And so there we go. And note, if you're paying attention here, that basically, like, even though we start by incrementing by 4, this subset that we get, you could have incremented by 2 instead. And that works out because 2 is the greatest common divisor of 4 and 6. 4 being the offset that we're using, and 6 being the length of the string s. Okay, but that's jumping ahead a little bit. Let's okay, so let's do some more things. Now we need a lemma. Okay. I'm going to stop here, and I'm going to probably make the start of the lemma like the start of a new video.